Hello. So we're here to wrap up the chapter on testing claims about proportions, and I think next we move on to other types of significance tests in chapter 10 and eventually the end of the course. But this lesson today is going to be all about the test for difference in proportions. And the notation can get a little crazy. And for someone like myself with dyslexia, sometimes I have to reword what I'm doing before I put it into the notation that we need to see for the significance testing. But that might be a me problem. I guess we'll find out. So our learning targets today look really similar to what we did with the single proportion test that we did in the previous examples. But this is going to be the difference between two proportions and comparing whether or not there was a difference. So for setting up the significance tests for P1 minus P2 is the notation they're using here for the general formula. In order for the null hypothesis to look correct for what we're going to use it today, it has to look like this. P1 minus P2 equals a hypothesized value. Now, generally, the hypothesized value is often 0, meaning that the null hypothesis is there's no difference between the two treatments or whatever we're doing. Not always, but often. So another way to write that is to simply say P1 equals P2. That's often the way my brain thinks about it first, and then I'll rewrite it as P1 minus P2 equals 0. And of course, as we set up the significance test, we got to make sure that we've clearly identified the parameter of P1 and P2 and what they represent, that they're the true value for whatever the parameter is. So let's jump into some examples here. We have an example about students who come to school without eating breakfast. So they have some data from two low-income elementary schools. We have a simple random sample of 80 students from one school, found that 19 missed breakfast today. And at school 2, a simple random sample of 150 students had 26 who missed breakfast. So more than 1,500 students attend each school. That's an important fact for us because we're going to have to use we're going to have to check that 10% condition in a minute. Do these data give convincing evidence of a difference in the population proportions at the alpha significance level of 5%? So state appropriate hypotheses for performing a significance test and be sure to define the parameters of interest, of course. So first, they have set up the null hypothesis to be P1 minus P2 equaling 0, meaning there's no difference between the two proportions. And then the alternative they set up as a two-tailed one, where they said P1 minus P2 does not equal 0, meaning there is a difference. They're not claiming it's one direction or the other. This is a two-tailed test, just like we did with single proportions. So here's the definition of those parameters. P1 represents the true proportion of all students at school 1 who missed breakfast today, and P2 would represent the true proportion of all students at school 2 who missed breakfast today. And those notational pieces, P1 versus P2, make sense because they called one and school 2. If you have some other context in your problem, feel free to change the subscript to something that makes sense for you. The only thing I would caution you is to avoid using anything that looks like the null and alternative hypotheses, because that could get really, really confusing. So the significance test begins by assuming that the null hypothesis is true. So we assume that P1 and P2 are the same. That's an important feature of what we're going to look at next, because we need a common value for these two parameters, and we're going to call it P, because when we go to find the test statistic, we need to have a common value, and we don't have that right now. So if we assume P1 and P2 are the same, that means we could kind of pool them together and create this new combined value of a proportion where I could kind of put them all together. And the logic of how we combine them makes a ton of sense. So if we assume that P1 and P2 are the same, then we should be able to just add up the number of successes from both of the samples and divide it by the number of individuals in both samples. So just make like a massive new super improved proportion, if you will, a combined proportion. So notice the notation here. They have P hat with a subscript of C, meaning they've combined them. They didn't want to use P for pool because P sub P is very confusing, plus a lot of giggles from high school students when you say PP. Aha, I know. All right, conditions for performing a significance test about a difference between two proportions. Oh, don't these look familiar? Now, it's going to get weird on the large counts condition, but let's look at it anyways. So the randomization, remember it's a two-parter. We need to determine that they are being randomly chosen from samples. And if you were sampling without replacement, we need to also check the 10% condition. I think I misspoke on a previous example on a lesson earlier maybe the previous lesson, 9.2, where I said, oh, they forgot the 10% condition, but I think that's because they were sampling without replacement, so my bad. So the large counts condition also has to be met, so we can say that we have a normal distribution that we could work with. So just like before, we need to check that all of these n times p's are at least 10. Now notice the notation here. We have n times this pooled proportion that we just calculated. And then same thing for the complement to it. So successes, failures, and then same thing for N2, successes and failures in reference to this new combined pooled proportion that we're going to have to use. And all of them have to be at least 10. So back to these children with their breakfast eating habits from these two schools. So now what we're going to do is check the conditions. All right, so be it. So first of all, the random condition, and these are independent random samples because it said they took a simple random sample of these students. So we're going to trust that they did that properly. Now, this is not being done without replacement. So, or sorry, with replacement. So that means we do have to check the 10% condition. They did tell us that there's more than 1,500 students at each school. So 80 times 10 is 800, so that's good. And then this is be 1,500, so we have less than 10% of the students that are being sampled from each school individually. So we've met the random condition. Now for the large counts condition, the first thing you have to do is find that combined proportion, because remember we need that statistic for our statistic calculations coming up in a moment anyway. So this is the first thing we have to do is find this pooled proportional value. So 19 and 26 added together is 45 over the total number of students sampled for the two schools, and they got this new proportion of 19.6% or 0.196. We're going to use that now in this lovely set of calculations, which I know nobody wants to excuse me, I got cold if you can't hear it. No one wants to have to write all this out, but it is super important, so just get over it. N1 times this pooled proportion, and then N1 times the complement of that proportion, N2 times the pooled proportion, and N2 times the complement of that pooled proportion. And looky there, they're all well over 10, so we are good on the large counts condition. That allows us to use the normal curve, or an approximately normal curve, I should say. So approximate with the normal curve. There, those are all the words I needed together. So just like in the previous lesson, we're going to find a standardized test statistic. This is a little weird for a difference in proportions though, because this is what it looks like. And as a child, I remember learning this going, this is really stupid. But remember, the parameter is not always a difference of 0. We often see that the difference is 0, but once in a while you'll get a weird example where the perceived difference in the null hypothesis is not 0, so just watch out for that. So the statistic is the sampling proportion subtracted in the order that you defined in the hypotheses. And then down here for the standard error calculation, they're using that, they don't have the notation here. I like this next notation, but it's coming up. Okay. They have to use the notation for that pooled proportion. That's the one we're going to use down here. But remember, we already did all that math where we found the pooled proportion because we were doing that for the 10%, or sorry, the large counts condition. Now it does have a note here. You're going to be tempted to replace P1 and P2 with the corresponding sample proportions, but those are not the same thing, right? P hat is the sample proportion, and I noticed in the formula here we don't have that hat, which means this is a parameter. So this is where we need to replace it with P hat sub C. Remember that guy? We just found that. And it was an estimate from our pooled data. So it's not necessarily a parameter per se, it's a pooled statistic, I guess. But either way, this is the formula we have to use. So again, I need to have a stinking formula sheet next to me, which I don't have, but I should go double check to see which version of this is showing up on our formula sheet. I have a feeling that's the one because that's pretty clear, but we'll see. All right, back to those kids. So explain why the sample result gives us some evidence for the alternative hypothesis. That's our first task. So remember that the alternative hypothesis was stating that the difference in the proportions is not 0, meaning that they are not the same proportion. So you could easily show that by just simply calculating p hat 1 minus p hat 2. So that comes out to 0.0642. So right away, I see that that's not 0, so that is favoring the alternative hypothesis. But do we have convincing evidence, which is the same question that we had when we did single proportion tests. Oh, so question B says calculate the standardized test statistic. Oh my gosh, statistic. I really got to practice that and then find the p-value. So first step, and we've already done this because we did the large counts condition, but you find that pooled statistic where you find the combined proportions, that 0.196, and you use that a couple places here in your z-score calculations. Use it right here and right here. So this is the proportion for p hat 1 minus p hat 2 minus the perceived difference of 0, square root. This is the standard error calculation down here. And again, I'm going to write this out and pretend like I'm doing it by hand, but really I'm probably going to do my calculator. We'll talk about that later. But we do get a z-score of 1.17, which is something I would have to write down on any free response answer anyways. So if I was using table A, then I would have to remind myself, oh, you know what I don't like here though, guys? They did not draw it. I wish they had. Anyways, if they drew it, they would have reminded themselves because it's a not equal to 0, they're going to have two tails. So you need to either find the area that is less than negative 1.17 or greater than 1.17 and then double it. So you're going to get a p-value of 0.2420. Now, if we used our calculator, and it's really nice since you already have the statistic, just to use the standard version of it where you have a mean of 0 and standard deviation of 1. Don't forget to double it though, because we have two tails. Either way, you get about 24%. And remember, our significance level was 5%. So what conclusion are we going to make here, guys? Well, because the p-value is greater than the significance level, we fail to reject the null hypothesis. There's not convincing evidence of a difference in the true proportions of students at school 1 and school 2 who skipped breakfast today. And that's that. So we'd either have to do more research, more data collection, or decide to change our test in some way if we were looking for some other answers. Again, that's not really how data is supposed to happen. So I mentioned the calculator, and you know I love my calculator. So I doubt anyone's surprised to find out that there is a test for this. So remember on the previous lesson, we had one proportion z-test when it was a single proportion, but here we have two proportion. So in two proportion z-test found in the distribution menu, they're going to ask you for x1, n1, so that's the first proportion for p1, and then x2, n2 is for p2. You decide what kind of a test you're doing. Is it not equal to? And then this is where kids sometimes get confused. We'll see in the next example, I actually write it where it's like, I think I mentioned this, like P1 equals P2 for the null hypothesis, and then my alternative is similar, and then I end up moving the terms around algebraically to get it to look like what the book wants it to look like. But don't fret about that. Just think about whether it's going to be greater than, less than, or not equal to. And of course, you have the option to either draw it or calculate it. I think I just calculated it. The drawing, though, remember, is really nice because it gives you a good picture, a visual. And then it also tells you the z-score, the test statistic, and also the p-value. So that's what we need for a free response answer. So if I was using my calculator to check that I've done this right, that's the route I would go. So here we do get a standardized test statistic of 1.168 with a p-value of 0.24. That looks familiar. So it's not cheating, it's using our resources. We still have to know what we're doing. Now here's the exam tip. The formula is a little kooky, and it results in a lot of errors. So people who try to use that formula, with the statistics, the p hat 1 minus p hat 2 minus 0 over the standard error, like a lot of kids screw that up because they don't type it in right. So they're going to say your teacher's probably going to recommend that you use your calculator. Heck yeah, I am. So I say we do a hybrid approach. I say we pretend like we're doing it by hand. Hey, if you're adventurous and have time, go ahead and try it. But we're also going to use the calculator, and I'm surely going to use that draw feature on my newer one. Make sure that you report, however, the what test you're using in the plan step, and then report the test statistic and the p-value in the do step. So there he be, the formula. It's a lovely formula, isn't it? Now, notice we had to calculate that combined proportion in order to pretend like we were going to use this formula. When I did the calculator, it never asked me for that because it does its own calculations for that. But where's my work? Back. Where's my proportion? It's at 0.196. So if I look at my calculator carefully, they don't call it p hat sub c, they just call it p hat. But looky there he is. Again, you have to show your work on a free response problem though, so you're still going to probably want to write that work out. It's not like that was horrible work, by the way. It's just the calculator, we're really going to use it as a way to check our work. And if it's a multiple choice question, all bets are off. Do what you want to do. High levels of cholesterol in the blood are associated with higher risk of heart attacks. Well, using a drug to lower cholesterol reduce heart attacks. So the Helsinki heart study recruited middle-aged men with high cholesterol but no history to investigate this. The volunteers were randomly assigned to one of two treatments. So here's some language from our sorry, I'm getting messages from my mother. These are same language that we've used in our, oh man, way back at the beginning of the course when we were in chapter 4 in the experimental design chapter. So you're going to see some things come back, which is why we started with that chapter with it being so important. Anywho, they were randomly assigned to the two treatments. 2,051 men took the drug gemfibrozil to reduce their cholesterol, and there's a control group who took a placebo. So during the next 5 years, 56 men in the gemfibrozil group and 84 men in the placebo group had heart attacks. So did the study give convincing evidence at the 1% significance level that gemfibrozil is effective in preventing heart attacks? Now, first thing I want to point out is that this is a serious study, and this is like life or death, literally life or death for people. And if they want to claim that this medicine is worth it, because I'm sure, like any medicine, there's also side effects. Their significance level is incredibly slim. So they're at the 1% significance level, and that's something that you will see in medical studies where things are, life or death. They want to have really convincing evidence, I guess is a way to say it. So once we perform this, we're going to interpret the p-value and make sure it's in the context of the experiment, of course. So we got to go through the whole process. Here we go. And it's that same process from the previous lesson. So we are going to state. So our null hypothesis, and notice the subscripts that they've used here are contextual. This is P sub G, meaning this is the proportion of the people who took gemfibrozil, and then P sub PL representing placebo. So that really helps the dyslexics of the world, that's me, because now I don't have to go back and try to figure out who's what. So the null hypothesis is that there's no difference, meaning the gemfibrozil group equals the proportion of the placebo group. So to make it look like they want it to look for this problem, they subtracted that over. That's how I think of it in my brain. Now, for the alternative hypothesis, they're trying to show that the gemfibrozil group has a lower proportion of heart attacks than the placebo group. So if you think about adding this back over here to this side of the inequality, that would say the gemfibrozil group is less than the placebo group, which is what they're trying to prove or find evidence for. So when they subtracted that term over, this is what it has to be subtracted in this order to be less than 0. Now, side note, if you reverse the order and you said placebo minus gemfibrozil, then you would reverse the inequality and you would have a greater than 0. So just make note of which way your inequality should be going. So now they define the parameters here, where P sub G is the true heart attack rate for middle-aged men like these who take gemfibrozil. So remember, just like our language with experiments, the experiment is only as good as how they've designed it. So this experiment, the results of it can only be applied to people who are just like these guys who have been in the test groups. And then for the placebo, that is the true heart attack rate for middle-aged men like these who take a placebo. And the significance level is 1%. All right, so there's our state. Here is our plan. So we're gonna say what test we're gonna use, regardless of what method you're choosing. You must say this. So a 2-sample z-test and then notate the direction in which you're subtracting them: P sub G minus P sub PL. They are randomly assigned to the groups, so that's been done. And then you'll notice they didn't bother with the 10% condition because they are not sampling without replacement. So we don't have to worry about that. I feel like I just said something backwards. My brain is so foggy right now. Yeah, we're good. Oh yeah, because they're all being used. Okay, we're good. All right. So large counts condition, that does need to be checked regardless, because we have to make sure we can use the normal curve. So we're going to find this pooled statistic by adding the, this sounds terrible to say successes as heart attacks, but the heart attack numbers divided by the total number of test subjects, and we have a new pooled proportion of 0.0343. So we're going to use that in our next step. Oh, I forgot to test them. So large counts. So the N is the 2051. So all of the what's it called again? Gimfibrazole group. So that's N sub G times this new pooled this pooled proportion. And then same thing for the complement to that, and same thing for the placebo group and the complement to that as well. And all of them are surely greater than 10. Okay, now we're going to do. So we have all of our pieces set up here, which I really like how they did this. You know, we have P hat sub G, P hat sub PL, P hat sub C. They can see all the work. It's all lined up. Here's the work for the test statistic in the order of G minus PL. And if they went through it and actually calculated it, this is the fraction they would have ended up with, and reducing down to a negative 2.47. But we could have also used a calculator, but you know my feelings on that. We're going to kind of fake it till we make it. So we're going to have the option at this point to use table A. I don't like that they didn't draw this. Remember this hypotheses, if I back up a minute, was that it was less. So you're going to be doing a left tail, which means when you use table A, you're just going to find your proportion that is less than z-score of negative 2.47, which is this. And if you use technology, you get the same answer. And if you've really used technology and you've done a 2-proportion z-test, you also got the same answer with all the pieces showing up as well. But I still want you to write out the work. I think it's great. So what's our result? We got a p-value of 0.0068. Which is less than the significance level of 0.01. So we have evidence to reject the null hypothesis. There's convincing evidence of a lower heart attack rate for middle-aged men like these who take Gimfibrazole than those who take only a placebo. And that's it. And that kind of ties back to our experiment language. You know, this can only be applied to men who are just like these guys that were involved in the experiment group. You can't apply this to how Gimfibrazole affects women or younger men. I feel like they, I don't know if they said the men's ages or not. I can't remember. I feel like there's more to this. Okay, so here comes the other part of this. Here we go. So assuming that the null hypothesis stated there is true, and that there is no difference in the effectiveness of the two treatments, there is a 0.0068 probability of getting a difference of Gimfibrazole minus placebo in a heart attack rate for these two groups of negative 0.0141 or less just by chance involved in the random assignment. Now, we got to dissect that a little bit. So where did this number come from is usually the first thing kids are wondering. So let's go back. Boop, 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 boop. Keep losing my spot. Okay. So this value is what we get when we it's when we subtracted the proportions. Where did I not find that? Oh, goodness gracious, Abruzzo. Oh, it's right there. Hello, I skipped right over it. So the subtraction of the two proportions in that order, this is the exact difference that they're referring to when they talk about the probabilities. So that's a little confusing, and I don't think I made it any better by blabbling just now. But you're going to have a probability of this tiny probability of getting that number or less just by chance involved in the random assignment. So what they mean by that, what they're stating by that is really the definition of a an error in your test of significance, that there is technically a chance that we're wrong, but it's pretty small. And we have enough convincing evidence to state that we have enough evidence to reject the null hypothesis. And that's where it kind of ties back. And it really ties back to those diagrams that none of you like to look at, those dot plots about, are these statistically significant or not? All right, sorry if that was clear as mud. I really babbled. Oh boy, that's really big on my screen. All right, so to study the long-term effects of preschool programs in poor children, they designed an experiment. They recruited 123 children who had never attended preschool from low-income families. And researchers randomly assigned 62 of the children to attend preschool, paid for by a study budget, and 61 to serve as a control group who would not go to preschool. This sounds sketchy. Oh well. One, don't you just love experiments on children? No, we don't. That's terrible. All right, one response variable of interest was the need for social services as adults. Okay, so over a 10-year period, 38 children in the preschool group and 49 in the control group needed social services. So, do these data provide convincing evidence that preschool reduces the later need for social services in children like these in the study? And justify your answer. And then based on your conclusion to number one, could you have made a type 1 error or a type 2 error? Explain your reasoning. And should you generalize the result in question one to all children from low-income families who have never attended preschool? Why or why not? So if you're working in those slides from my class, the next page shows you all the answers. So try not to look at it and pause the video and try some of these. Regardless, I would like everyone to pause the video and try jotting down some things here. But we are going to go look at the answers now. So do we have convincing evidence? Well, here's number one. And remember, we got to go through the whole process, which I know is annoying, but we do. So we want to test the null hypothesis, which states that there's no difference between P1 minus P2, and the alternative hypothesis, claiming that the need for social services in the second group is less than the need for social services in the first group. So then they define the parameters. P1 is the true proportion of children like the ones in the study who attended preschool that use social services later. And P2 is the true proportion of children like the ones in the study who did not attend preschool that use social services later. And we're using a significance level of 5%. Did they state that? No. So I guess we just made that up. Now, when in doubt, 5% is a good number. So go with 5%. That's very accepted in other communities other than like the math community and biology. They use 5% most of the time. And psych. All right, so now we're going to plan it. We're going to do a two-sample z-test for the difference in proportions. They were randomly assigned to groups. So that's the randomization issue. And then they are checking, oh, they didn't have to worry about the 10% condition because there was no need for the independence, the with or without replacement issue because they assigned all of them to a group. And then where are we at? Oh, the large counts condition. So they had to find the pooled proportion. So they added up, again, I don't like the way I'm phrasing this, but the successes, if you want to think of it that way. So the number of people who needed social services later in life divided by the total number of people, and they got this new and improved proportion, which is the combined or pooled proportion, the 0.707. So then they checked all four things. So N1 times the pooled proportion, and then N1 times the complement of that, and then same thing for N2. All of them are greater than 10. And yes, that is very annoying to have to write out, but you have to write it out. So now we're on the do stage. So here's our three proportions. We have P1 hat, P2 hat, and the combined proportion. So plugging that into our formula where they did P1 minus P2 minus no difference, divided by the standard error, yada yada, got a z statistic of negative 2.32. Again, could have done that on the calculator. Definitely would have done it on the calculator to check all that work. That would be a real bad day when you get to the end of that problem and you realize you did something wrong. That's a very Abruzzo move to do, by the way. Drawing it out, I think, also is important because remember this alternative hypothesis is less, so we're left bound on the curve. I think that helps. Oh, speak of the devil, there he is. So our calculation is going to come up next. So they're going to want you to use that z-score either using table A or technology to find a p-value, which is 0.0102. Ooh, dang, that's close. Oh, never mind. It's not close. I thought we were doing 1%. We're doing 5%. So our p-value is less than our significance level, which means we can reject the null hypothesis. So there is convincing evidence that the true proportion of children like the ones in the study who do not attend preschool that use social services later is less than the true proportion of children like the ones in the study who do not attend preschool that use social services later. That is an epic mouthful of words. I feel like they could have condensed that a bit, but that's okay. In other words, oh, here, children like those in this study who participate in preschool are less likely to use social services later in life. That makes a lot more sense. Thank you. All right, so what was question two? I already forgot. Based on your conclusion to one, would you have made a type 1 error or type 2 error? Oh, could you have made? So, because we rejected the null hypothesis, that means we do run the risk of creating a type 1 error where we would find convincing evidence to reject the null hypothesis, but actually um, the null hypothesis was true. So, what that would mean is the true proportion of children, like the ones in the study who attended preschool, um, sought out social services at the same rate as those who didn't attend preschool. So, was that a risky error because of the way the experiment was designed, as opposed to a type 2 error? Should you have changed the way you've done your test of significance based on those two? You would have to think about that. And should you generalize the result in question one to all children from low income families who have never attended preschool? So, no. That was a quick no. Remember our words about experimental design. The children that participated in the study were recruited from low income families in Michigan, not randomly selected. So they cannot be generalized to all children from low income families. Low income families in Michigan are different from low income families in Denver, who are different from low income families in Paris. So we cannot generalize this to every single low income family. It's only like those in the study, which in this case were from Michigan. And that's that. All right. So, a lot of words, like everything else in stats, a lot of words happening there. The difference in proportions calculation for significance, it was very a la difference, single proportion calculations, but we had a difference instead. We had to find this new pooled proportion. That was kind of new. Um, but again, we need to revert back to our formula sheet to make sure we know where we're looking on our formula sheet and how it can help us when we get to a case of, being in the middle of an AP test and not sure what sort of formula to use. The other big key difference is to notice that we were using a two sample proportion for two sample z-test for proportions, difference in proportions. So that means we had to use a different approach on our calculator, meaning a different command. The good news is the calculators, because of the new design for the programs, they are like fill in the blank style, I guess. So if you pull up the wrong test, basically you're either going to have too much or too little information and you won't be able to use it. So that'll be your first hint, like, oh man, I think I'm using the wrong test. I don't have a P2, or vice versa. So, all right. Thanks for watching. Go, where's my pause button? Good luck, everybody.